kinematics for interview preparation. So, what is kinematics? Kinematics is a study of fluid mechanics concerned with the motion of the objects without the reference to the forces which causes the motion. So, in this study, we are not concerned about the what causes the motion of the fluid. We are only concerned how the motion is happening, which basically needs velocity, acceleration, momentum, and discharge. This four quantities explains how the motion is happening. Okay, so there are four types of flow of motion. Let's see, I'll show you. There are four types of flow of motion. First is the linear transformation, linear deformation, angular deformation, rotational. So, do you consider fluid particle or fluid element, and why? So, in this case, we basically consider fluid element. Fluid element is nothing but a lump of fluid particles, and we use it because fluid particles doesn't have any size or a shape, but we can have a fluid element which has a different, because we are describing the element, so we can have the size for that fluid element. So that's why we are taking fluid elements for this study of flow of motion. So the first one is linear transformation. So do you consider fluid particle or element same, and does the shape or axis change? So in linear transformation, the fluid element moves but it doesn't rotate or change its shape. So the axis of even the axes are parallel to each other after the movement. The second is the linear deformation. So in linear deformation, the shape changes linearly in a particular direction, but it doesn't rotate, and the axes are also parallel. The third one is angular deformation. In angular deformation, the fluid element deforms at certain angle, phi or theta, at given time from t to t1. In rotation transformation, the element rotates with respect to an axis. So that is the definition. So the next one is the type of flows. So that we will discuss here. So in type of flows, which flow variable or parameter used differ steady and uniform flow. So we'll see that. So there are basically two important variables, time and position. So when we are studying about the type of flows, we have to recognize that if time is constant, the position is changing. If position is constant, the time is changing. So in the first type of flow is steady and unsteady flow. So if the flow parameter of the fluid flow doesn't change with respect to the time, that means time is constant, then such in a particular section, then that kind of flow is called steady flow. That means if a given fluid parameter, for example, one of the fluid parameter is the velocity. If the velocity doesn't change with respect to the time at a given section, that means that flow is steady. Otherwise, that flow is unsteady. The second one is uniform and non-uniform flow. So let's see what is written here. Steady and unsteady flow. In a given section of a steady flow, which parameter doesn't change? So in this thing, time doesn't change. So in a given section of the fluid flow, which parameter are considered and which is kept constant? So in uniform non-uniform flow, you will see that if the flow parameter of the fluid flow doesn't change with respect to the position when the time is fixed, it's called uniform flow. That is, if at time t in section 1 and 2 here, the velocity here and here are not same, but here and here are same. So in this thing, if the velocity doesn't change with respect to the position, that means it's a uniform flow. So in this case, this U3 and U4 are uniform flow because with respect to the position, if I change from 3 to 4, the velocity doesn't change. In this case, it's called uniform flow, but here it is changing. So in a given section, if the position is not changed with respect to the velocity, if the velocity doesn't change with respect to the position, it is called at a given time, it is called a uniform flow. Okay, next one is the laminar or turbulent flow. Which one is a steady flow? Which one is a random or unpredictable? Which property decides laminarity or turbulence? We will discuss this. And okay, so there are some examples. So what you can say about the river? River is steady and non-uniform flow. Because the speed of the velocity of the river doesn't change with respect to time, but it changes with respect to the position because the beds are non-uniform. Canals are steady and uniform because both the velocity doesn't change with respect to time and the position because it's like a big concrete pipe. And normal pipe flow. Pipe flow is unsteady and uniform flow. Uniform because the velocity doesn't change with respect to the position, but it is unsteady because it changes with the time. Because okay, here in area 1 and 2, the velocity doesn't change with the time. As the water level is decreasing. See, sorry, it changes with the time because if the water level is decreasing, then the speed here in this area will basically decrease. That's why it is unsteady. But in this particular section, it is uniform because with respect to the position, this velocity doesn't decrease. So next one is the laminar and the turbulent flow. So laminar flow are basically steady flow. The particles move parallel and happens due to the viscosity. So in a motion of a fluid, we basically assume that the fluids are traveling in layers. So when we see that if the velocity of this particular fluid element in this layer and this layer are almost same, the velocity is same, and they don't, and both layers don't collide with each other. At that time, we call this as a laminar flow. If this collides, if the layers mix up, then there is a disorder or zigzag mixed flow, and that time we call it as a turbulent flow. And the reason behind of this laminar flow is because of the friction as well as the viscosity of the fluid. And this kind of laminar flow are more predictable. Uh, because the behavior of the fluid motion is linear, or it's parallel in layer, while the turbulent flow the motion is very random and it's unpredictable. So basically this happens due to the less viscosity or maybe high velocity of the fluid motion. So next one is the compressible and incompressible flows. So what can you say about compressibility with respect to density, bulk modulus, liquid solid gases? So first we will see the incompressibility. So when the density of the fluid increases, density of any matter increases, its compressibility decreases. That means in this case the density of the gas is very less as compared to solid as compared to the liquid. So that means it is highly compressible. That means it's least incompressible. While solid in normal situations can be compressed, while the liquid, as the density doesn't change with respect to the change in pressure, it is considered the most incompressible with respect to the solid. So as we know from the bulk modulus that the change in pressure by the volumetric strain can be described as the volumetric density. When the pressure changes, the density doesn't change. At this case, change in pressure divided by 0 equals infinity. This means that the bulk modulus is infinite for the liquids, and compressibility is inverse of the bulk modulus. It means that compressibility of liquid is 0. Okay. Then let's talk about the rotational flow. So rotational flow is basically microscopic in nature. We can't see by naked eyes. That means that the fluid element rotates about its axis, and this fluid rotating rotates about its axis. It's not observable, but when these two fluid elements rotates counterclockwise, that means in opposite direction, they don't cancel out. Basically, they increase. That creates a vorticity. The microscopic phenomena of rotation, if we take the double of rotation like this, the double of rotation or the angular velocity is equal to the vorticity. That means the ohms. Ohms is equal to 2 times the angular velocity. If the vorticity times the area loop or in certain area gives the circulation. For example, and this is a mass phenomena. It's a microscopic phenomenon. For example, we have a tea particles. We put a tea in the water, and you see that due to the heat, the particle of the teas rotate, and this is due to the circulation because of the vorticity times the area loop, and this creates a large microscopic phenomenon called circulation. And in rotation, the average angular velocity can be described in a matrix form like this, and The total angular velocity is described like this. For each component of the angular velocity can be taken from this matrix as by taking the cross multiplication for each component, and we say the um, fluid flow is irrotational when the total angular velocity is zero, or all the components of the angular velocity is zero and the total angular velocity is zero. So next is the vortex flow. So rotational flow, is it observable? No, it's not observable. How does it rotate? It rotates due to the twice the because of the circulation, and that circulation is due to the vorticity times the area loop, and vorticity is nothing but the twice of the angular velocity. How to calculate the average angular velocity, as we have seen from this matrix calculation? Where is it? Here. From this matrix calculation, we can actually find the average angular velocity. The condition for irrotation flow, as discussed, it should be zero. So in this thing, there are two main phenomena: vorticity circulation, as we have seen, T test in the water, reason behind circulation, as mentioned earlier. So next one is the vortex flow. Is it observable? What kind of motion does it show? Let's see. Vortex flow is basically a macroscopic phenomenon. It can be observed by naked eyes, and it's a bulk or mass phenomenon. It rotates in a curved path. So let's see. So there are this motion is nothing but a vortex or a full time a curly a measure of the fluid. Okay. So there are two type of vortex flow. There is a forced vortex flow, and the other one is the free vortex flow. So in the forced vortex flow, is the is torque induced in this case, or the constant angular velocity? What is the constant angular velocity formula? Tangential velocity formula. Or what we can say about the graph of velocity versus the radius? Yes, the forced vortex flow is of does contain external torque. For example, a fan or runner or impeller. Okay, this kind of means the torque, we apply the torque to create the vortex. So the constant angular velocity formula, the constant angular velocity formula is 2 pi n by 60. Okay, and the linear velocity, the tangential velocity formula is v is equal to r times omega, and v by r is equal to constant. So for vortex, the angular velocity should be constant. And in this case, for the forced vortex, the graph v times r is linear, as the angular velocity is constant. At r is equal to 0 or v is equal to, at r is equal to 0, the velocity is also 0. That means the fan, if we touch the fan at the center, there is no force, there is the least force there. But if we go at the end of the tip of the fan, we see that the force is very high, the velocity is high at that point. The radius increases, the velocity increases, and at the radius is equal to 0, the velocity is 0 basically. So the other one is the free vortex flow. So in this case, is the torque present here? What generates the vortex here, and what is the formula relation between the V and R, graph of V and R? In this free vortex, there is no external torque. For example, whirlpool, wash basin, river, or pipe. As you can see in the wash basin, it is a hemisphere, half hemisphere. And in this case, if we put the water, it just flows in a circular path, and you can see in the outside, when the radius increases, the velocity is basically, the torque is basically less. When it goes to the center, it means the wash center, you can see the torque is very, very high at that point, or whirlpool basically happens in the oceans or seas. You can see at the center, the torque is very, very high. The reason behind is that the torque is equal to the change in angular momentum. Angular momentum is nothing but L is equal to V, mv, that is momentum times the R. P is equal to linear momentum times the R. So change in angular momentum is basically torque. So therefore, torque is zero. If the torque is zero, that means the angular momentum is constant. So that means mvr is equal to constant. Or we can say that v is equal to v is directly proportional, is inversely proportional to the R. That means if the radius increases, velocity decreases. As I said, when velocity increases, when the radius decreases, it means in the performance you see that when the radius is zero, the velocity is very, very high. So in this case, as there is no torque, applied, that's why the torque is zero. That is why the angular momentum is constant. Okay. So next one is the uh, Reynolds number. We will come to this. So Reynolds number. Which two forces are taken as a ratio? What is the Reynolds formula? What are three parameters decides the flow type? How to create a laminar or turbulent flow with respect to the Reynolds number? So Reynolds number is basically the ratio between the force of inertia by the force of viscosity, viscous force. So in fluids, the inertial force is equal to mass flow rate times the velocity, and mass flow rate is nothing but the q times the density, and discharge, that is q is equal to a times the velocity. When you put all this relation here for inertia force, we get the density times the area times the velocity square. This initial force. And for the viscous force, we get the formula from using the Newton's viscosity law. That is, the drag stress is equal to mu times the velocity gradient, and the drag force is equal to drag stress times the area, and we get this formula here. So this is the differentiating velocity gradient at a particular time. The velocity by, we get the v by y, and y is basically the distance, that the diameter of the pipe. So we put the t here. When we create the ratio, that is the Reynolds number is equal to inertial force by viscosity force, when we derive the equation, we get such a relation. Density times velocity times the diameter by the mu, that is the dynamic viscosity. And we know that the coefficient of kinematic viscosity is equal to gamma is equal to mu by rho, and from this we can get such a relation. Okay, and in the pipe flow range, we say the flow is laminar when the Reynolds number is less than 2000, and it is turbulent when it's more than 4000. In between, it's called transmission phase, and we say that this transmission is basically, let's say the transmission Reynolds number is 3000. We say that this is a laminar or turbulent with respect to the initial phase of this. If the initial phase was laminar and it gradually increased the Reynolds number, then we say that it's a laminar transmission. If the initial phase was turbulent and decreased later, then we say it is a turbulent transmission. For the flat plate, the flow range for laminar flow is less than 3 lakhs, and for the turbulent is more than 5 lakhs. So basically, three parameters which decide the flow type. The first one is the gamma, that is the kinematics viscosity, which is the fluid property. Second one is the geometrical property, that is the diameter of the pipe. Third one is the velocity, which is the flow parameter. So if the kinematic viscosity increases, the velocity decreases, then that means the Reynolds number will decrease. It means it is a laminar flow. If the velocity increases and the viscosity is constant, then the Reynolds number will increase, and in such case it is called turbulent flow. Okay, so these are three parameters which decides how it becomes the laminar flow or turbulent flow. Okay, so now the 1D flow. So let's talk about 1D flow. 1D flow in fluid for the solids. So 1D motion in the solids is basically dependent upon the one particular direction. The velocity of a velocity motion, the velocity of the solid body does change with respect to one direction, but doesn't depend on the other. That's because the solid body shape is fixed, but for the flow of the fluid in 1D motion, the motion basically depends upon the both axes, x and y, for the x and y for the 1D motion, because change in y direction changes the velocity in x direction. So that's why the velocity in 1D is a function of x and y. Okay. So next one is the continuity equation. So continuity equation is basically an important equation, as you can see from this picture. So there are some questions to be asked in continuity equation. What is considered here? What kind of liquid is considered? What does it say about the discharge? If the flow is continuous, what does it tell about the flow? So continuity equation is basically the mass fluid rate conservation equation of the fluid flow. So that means the mass flow is conserved. That means the mass flow formula is rho times q, and q is a times v, so rho av. That means the mass flow rate at the both the section is same. That means the change in mass flow rate is zero in this both the section. That's what it means, the conservation of mass flow rate. So if it has to be same, that means the condition is the mass flow rate at the both the section, that is m1 and is equal to m2. And it will be same when we put this equation here, substitute here, we get that the discharge in the both the sections are equal. That means here the Q1 and Q2 are same. And this is the 1D continuity equation. Q1 is equal to Q2. So what is conserved here? The mass flow rate is conserved here. What kind of liquid is considered? We considered incompressible. That means the density of the fluid doesn't change. And what does it say about the discharge? Discharge is same in both the section. If the flow is continuous, what does it tell about the flow? If the flow is continuous, that means if this flow is continuous, what does it tell about the flow? The flow is continuous. Obviously, it is incompressible and it is continuous. That means it is a steady flow or laminar flow. We can't say laminar, but we can say it's a steady flow because the Q is same. That means the velocity V1, V2 is same. The velocity, if the velocity doesn't change with respect to the position and time, that means it is steady and uniform. So it is steady and uniform flow. So in 1D, what is the equation? As you can see, Q1 is equal to Q2. What can you tell about the 1D continuity equation? So 1D continuity equation means the mass flow is same in both the sections, and the discharge are both same, and this is basically incompressible, steady, and uniform flow. So what about the 3D equation? The 3D equation is the important one, and if the fluid flow is steady and incompressible, then you will see that. So continuity for 3D equations. So in this case, we consider basically the fluid elements because it can be defined in its shape, in size, but the fluid particle doesn't have any size. There can be many fluid particles inside the fluid element, as we had discussed earlier. So what is the total velocity for this fluid element? So V is equal to the components of the velocity. So this is the basically continuity equation for the 3D. So change in density with respect to time plus partial differing velocity components, and as a total that is equal to 0. Okay. And in this case, we consider we can basically transfer this 3D equation to the 2D equation. For this, we have to assume or consider that the flow is steady. That means the density doesn't change with respect to the time, and the flow is incompressible. That means the change in density is 0. And it is a 2D. That means the third velocity component is not applicable. So when we put that, this two terms cancels out, and we finally get that curly u by curly x plus curly v by curly y is equal to 0. This is the 2D continuity equation. So there are three assumptions. That means the fluid is steady. That means nothing changes with respect to the time. Then it is incompressible. That is the velocity doesn't change with respect to the time. And then it's a 2D flow. So these are the three conditions for the 2D equations. And as you've seen that if the fluid is steady and incompressible, then it becomes a 2D equation. Okay. And these are basic assumptions for the 2D equations. So let's go to the velocity of the fluid element. So as we've seen that the total velocity or total average velocity as a vector form is this. When we want a scalar form, it is described like this: root of u square plus v square plus w square. And for each component is basically a function of x, y, z, and time. For each velocity component is different, is a function of these three components. And next one is there are some questions asked here. What is the total velocity of the fluid element of the fluid? Vector scalar form we have discussed. And what is the local acceleration, convertive acceleration? So let's see. So acceleration of the fluid element. So average acceleration vector form is ax plus ay plus az. The scalar form magnitude is same as the velocity, root of ax square plus ay square plus az square, and for each component ax is equal to differentiation of du by t. But when we take the partial differential form of the acceleration along the x-axis, that means curl u by curl t. Curl u by curl t is basically the local acceleration, and the acceleration x x component of the acceleration in different directions is called convertive acceleration. That is u times curl u by curl dx plus v times curl u by curl dy plus w times curl u by curl z. So this is basically called convertive acceleration. This is called local acceleration. Okay. So let's go to the velocity potential function. So this is an important function. This is not a physical quantity, neither it is a so it's basically yes, it's a vector quantity because it shows the direction at which the flow will flow. And we will see the examples of the potential function and how to find the velocity from the potential function. So for any flow of fluid or energy or temperature, there is a requirement of a potential gradient or potential difference. For example, to heat energy flow, there should be a change in difference in temperature. When there is a difference in temperature, the heat flows from high temperature to the low temperature. When if the air have to flow, that means there should be a pressure gradient, pressure difference, high pressure to low pressure. If the river has to flow, there should be gravitational potential difference. That means high gravity to low gravity. Okay. So that basically it means the potential difference leads to some kind of flow of energy, or that of the flow is, and that kind of flow is represented as wave function. We will see that later. So basically, if we have a potential differences of temperature like this, the flow will happen from high temperature to low temperature, and temperature, pressure are basically the potential functions. Okay, so examples of potential functions are temperature, pressure. Okay, and these potential functions can be used to find the flow parameter, that is velocity along the axis u, v, and w. So how do we find it? The velocities from the potential function. So u is equal to negative of curly v by curly x, and v and w are as such. So other questions of potential gradient are that what does the potential difference generate? 3 examples. How is the flow presented? So as we have seen earlier, potential difference generates some kind of flow of energy. What are 3 examples? 3 examples are the heat energy, air velocity, river flow, and how is the flow represented? Diagrammatic equation. Diagrammatically, this is the diagram, and by equation, this is the equation. And let's talk about the flow behavior with respect to the potential difference, potential function. So the questions are: in which direction the velocity increases? How does the Laplace equation, and what should satisfy it? What does it tell about the flow? What does the angular velocity have to do with potential function? What does it indicate about the flow field? Okay, so the first one is that the potential function decreases with the decrease in potential function, the flow increases. That means if the potential function like this decreases, the flow of the velocity, the fluid flow direction is this. The fluid flow velocity increases in this direction. Okay, how do you know if the flow is continuous or steady? That is continuous and steady and incompressible with the potential function. How do we know the flow is continuous with respect to the potential function? So let's assume the 3D equation of the continuity 3D equation to be steady and incompressible. If it is steady and incompressible, that means the component curly rho by, that is the change in density with respect to time, goes off, and we have such a parameter. And as it is incompressible, that is the density doesn't change with respect to the time or such. And in this case, we get such an equation. And as we know from the equation of the velocity with respect to the potential function, we put this equation here in the continuity equation, and we get such a representation. And this representation can be shorted out like this, and this shorted out equation is called the Laplace equation. If this potential function satisfies this Laplace equation, then the flow is continuous. That means it is steady and incompressible. Okay, and how do we say that the flow is irrotational with respect to the potential function. So to flow should to be irrotation, that means the angular velocity should be zero. That means let's say along the z-axis, the angular velocity should be zero, and the angular velocity on the z-axis is represented like this, which is equal to zero. And when you put the representation of the velocity function in this equation, we get the angular velocity. So if the fluid flow, if in a fluid flow, if in the flow field potential function exists, then the flow is irrotational. If in the fluid flow, if it's going, if the potential function is existing, that means it won't rotate, because for example, if you're rotating and you get a sudden push, that means the rotation will stop, right? So it's the same thing. If there is a rotation, at that point there is no potential function. Okay. So the next thing is the stream function. As we know, the stream function is nothing but the direction of the flow. But what is a streamline? Streamline are basically the line of path followed by the fluid particle one by one. Consequent particles trace the path of the previous one. So if the particles are here, the next particle is also pass through this. So when certain particles pass through a particular point and we track it, and at this point the velocity, velocity tangent at this particular point will be same for all the particles. And when we track all these particles, it creates a streamline. And no both streamlines will be perpendicular to each other. They're all always parallel to each other. So the tangent line gives the direction of the particle at the streamline. Okay. So how to find the velocity from the stream function? How does the stream function describe? Is described, and equation for velocity component with respect to the stream function. We'll see that. So stream function is basically described like this, curly by curly x. It is described like this. So the 2D continuity equation, which is this, when we put these terms here inside the 2D continuity equation for steady and incompressible, when we put it, and when we see that if the stream function exists in the flow field, it means it is a continuous flow. And when we want, when should we say that it's irrotational? When the angular velocity is described like this, and we put these stream function values inside here, and we get a Laplace equation. If the stream function satisfies the Laplace equation, then we say that it is a irrotational flow. Okay. It is what creates the streamline? How does the particle travel in the streamline? How to find the velocity direction? So velocity direction is basically the tangent of the particle at that location. Streamline is how to create streamline? A particle which is moving along the same location. Those particles which are moving along the same location, we trace that, and we create a line. How does the particle travel in the streamline? They always travel in parallels, and no two streamlines are perpendicular or coincide with each other. So, what are flow behavior with respect to the stream function? Is it defined for 2D flows? No, it is defined only for the 2D flows, not for 3D flows. From 2D continuity equation with respect to the stream function, what does it indicate about the flow field? It indicates that it is a continuous flow. If the stream function exists in the flow field, which means it is a continuous flow. How to find or satisfy the Laplace equation? If it satisfies, what does it tell about the flow field? How to find? We use the irrotational flow condition, and we put the Laplace variables inside it. And if the stream function value satisfies the Laplace equation, it means it is irrotational. That's it. Simple. So when we compare both this velocity function and the stream function, if the velocity function exists in the flow field, it is called irrotational. If the stream function exists in the flow field, it is called continuous. This means it is steady and incompressible. That means steady means the flow parameter doesn't change with respect to the time. Incompressible means the density doesn't change with respect to anything. Density of the fluid doesn't change with respect to the time or the position. If the velocity function as well as the stream function exist in the flow field, we get a flow net. We will see that later. So the question is that what is the difference of stream function gives? If you have two stream functions like this, what is the difference gives? The difference of the two stream function gives the discharge by the width. Okay, it's the same thing. The difference in the stream function gives the ratio of discharge over the width of the stream function. So next is what is flow net, as we discussed earlier. Flow net is when the velocity potential function and the stream function both exist, and always the streamline and the potential line are perpendicular to each other like this. So as the potential function decreases in that direction, the stream function happens, and the stream function and the potential function are basically perpendicular to each other, and this we called as a flow net, which is also basically grid-like structure. And we can also have a circular kind of structure. If we have circular potential lines like this, and when we go into the center, the potential increases. If it is increasing in this direction, that means the streamline direction is like this. That means the streamline directions are outwards. So this is circular flow net. Okay. So thank you.